Probably like.
Okay, let's get started. So, we talked about transformers. We introduced transformers, and we always said they have a huge advantage of stepping voltages and currents up or down. And then we also saw that they reflected impedances up or down by not by the turns ratio, but by the square of the turns ratio. And so, if we want to do some calculations for equivalency, it makes it much more difficult to do that because now we have a generator here with a transformer and some sort of a load over here to actually calculate what the current is out of the generator on the low side of the transformer. Then we're going to have to reflect this impedance using the turns ratio, right? So that makes the calculation a little more complicated, but not incredibly more complicated. The other thing is, what if we have more transformers? We put the load, then we have to do it twice. And what if you have a system with millions of transformers and millions of loads? You have to reflect those impedances up or down. And so what we're going to do today is we're going to develop the concept of a per unit, which is just another way to say ratio, a fancy way to say ratio, essentially. But we're going to do everything in per unit or as ratios based on some typical or base quantities. And what we're going to see is if we do repeated calculations on systems, then we're going to find that per unit actually makes things much, much easier. And so why do we have to spend so much time doing per unit? Because that's how the utility world works. If you remember the homework assignment we gave last week, if you flip over to page 10, you'll actually see some Z data as a percent. There's no units associated with it, right? It's not an ohmic value. It just tells you what the Z of that piece of equipment is going to be. And the reason we have to do it on transformers primarily is because if this transformer, which if we simplify it down, looks like that, right? Remember, if the equivalent transformer is on this side, these resistances are going to look, or impedances are going to look very different than if we have something like this, right? So if we have our impedances reflected to the high side of the transformer or to the low side of the transformer, we would have to use different impedances. And so what the manufacturers do is they don't care, because what we're going to learn is if you set up your per unit correctly, the impedances on both sides of the transformer are 9.36 or 9.4 or 9.51. So when somebody sells you a transformer, they stamp on the nameplate, they stamp on the percent Z value, and it is applicable to both sides of the transformer. You're not telling it, okay, it's 3.76 ohms on the low side or 22.95 on the high side. You just give it as a per unit number. And because it's so essential to do that for transformers, we also do it in generators. And that's pretty much typical for what we would do for nameplate data. Okay, transmission lines, normally we have to actually calculate what those impedances are. So there's no per unit on those. There's also no equipment base, and we'll learn what an equipment base is. So transmission lines typically don't have a per unit value. But because the transformers and the generators are done in per unit, you convert them to per unit quantities no matter what. Okay, so what essentially is a per unit? It's just a ratio. You have a base quantity. Like I like to use the example, how much gas is in your tank? Somebody volunteer. How much gas is in somebody's tank? Like 14 and a half gallons. That's what currently you have for gas. What's that? 10 gallons. So you tell everybody that my tank has about 10 gallons of gas. Is that how you typically say how much gas is in your car? What do you typically say? Half a tank, quarter of a tank. Do you really care that there's 10 gallons?
No.
No, you just know where that needle is, or maybe you have an analog, right? You just know that that is half or three quarters. That's maybe 100 miles or 200 miles. It doesn't actually say on your gas gauge it's 5 gallons or 3 gallons. So you do it probably more often than you realize when you use ratios. If you work in the process control industry and chemical engineering systems, they have very large tanks for a lot of their processes. They don't talk about how many gallons are in the size of their tank, because if you have a 1,000-gallon tank, do you really care that it's 826 gallons in there? Or do you care that it's 82.6% full? 1,000 gallons is easy, right? What if it's like 7 gallons or something like that? You just get a better feel for, hey, the tank is half full, 3/4 full, 90% full or something like that. It's much more comfortable for us to do things. And another one, which is a lot more subtle. Anybody here been in the emergency room recently? One person? Remember the little pain threshold measurements there? Scale is 0 to 10. Why do they do that? Because it's your perception of what it is, right? You can't put it as a 9.6 on the Richter scale or whatever scale it is. You just say it's equal to 4 or an 8 or whatever it is, because it's based on your personal experience. So you can't measure that. You can't quantify it. It's much easier for us to quantify those things. Now, that doesn't always apply, right? Because when we're driving down the road and the speed limit is 65 miles an hour, and I'm sure all of you are law-abiding citizens and you're driving right at 65 miles an hour, not a mile per hour more, especially at the top of campus, right? Where they have the police stationed outside the sign now that tells you better slow down. So you'll notice a lot slower. I don't know if anybody's noticing that, but there have been police actually stationed at the top of campus to make sure you're not speeding. But when in that case, you don't have a range. You don't know how fast your car is going as a ratio, right? It's not based on a full speed of it. So in that case, you would actually use miles per hour. But for most practical purposes, if you could do things as ratios, if you know what something is at full out and you operate at full out at 50% of full out, you can get a pretty good sense of what's going on.
That could be really good. People say my car can drive top speed in
300 miles an hour?
Yeah,
You got a nice car.
But then driving at 30, that's a waste of my energy.
You mean it's the speed?
The speed, yeah.
What if the speed limit is 30? You don't want to travel 300 miles an hour in a 30-mile-an-hour zone. That would not be a waste of the speed on the car.
Speed.
Yes, you need to go on the track if you're looking for something like that. So, but typically that's what we would do. So it's just a ratio. Your actual quantity divided by the base quantity. Okay. So here's the process. It's a very process-oriented thing. This is for single phase equivalence. You're going to pick a single phase power base. Why do you think we'd start off for a single phase power base? Any ideas? Why is that A number 1? Does a transformer change the power? When you run power into a transformer, does it go up or down?
No.
No, we assume it's constant, right? So you pick one base for your entire system because that lives everywhere in your system. Transformers have no impact on it. So you pick one base. Oftentimes it's 100 MVA for like the typical utility system. That actually is a 3-phase base, but we'll just assume it's 100 MVA for the time being. And then that applies everywhere. So you pick one of those. Then your next step is to pick a single voltage base at a particular location. Why at a particular location? Because as you move through transformers, that voltage base goes up and down, doesn't it? The transformer does change that voltage. So if you have a 100 kV system or 100 kV transformer that steps down to 20 kV, if you're running your system at 100 kV, on the low side of that transformer, the voltage would be a nominal 20 kV. But if I did it as a ratio, a per unit, my voltage on my high side is equivalent to 1, right? It's 1 per unit or a ratio of 1. And on the secondary side, what would the ratio be for that voltage? It's still 1, right? Because it steps it down to 20 kV, that takes that 1 and steps it down to 1. Because your base has now changed from 100 kV, your voltage base has changed from 100 kV to 20 kV, all right? So you can actually, when you set up your systems, you can get rid of all the transformers, except for maybe the phase shift. So oftentimes when you represent a power system, when you're doing calculations, it's all just impedances and sources. There are no transformers anywhere in the diagram because I don't want to do the reflecting impedances back and forth. So I pick one voltage base. Oh, and I should apologize. I have a pretty good cold, so I've been coughing a lot and sniffling and sneezing. So I apologize for people listening to the audio or in the classroom if you hear me hacking. It's not intentional. So I have a voltage base, I pick one, and then everywhere I go up or through a transformer, I have to calculate the new base. How do I calculate the new base? I just use the turns ratio. The turns ratio will step it up or down. So I'm going to pick one S base, I pick one V base, and all the other V bases on the other sides of the transformers are going to be calculated off that one V base. All right. Then if I need to, I'm going to calculate my impedance base because, again, I don't want to calculate transformers impedances. I want to go ahead and take those to per unit. So I'm going to take VB squared, which is my voltage base squared, divided by my S base. What does that equal to? Well, VB squared divided by S base is just another way to say VB divided by, how do I set this up? So that would be V times I. But I want my ZB, which is V over I, and S equals V times I, correct? So if I solve this equation for I end up with I equals S over V. I substitute that into there, and I get VB squared over S base. And the reason why we use VB squared and S base is because, have I picked any of the I bases? No, those are going to be calculated from SB equals VB times IB. So I haven't calculated any of those. So up until step 3, I don't even know what my I bases are. Okay. So my equation for calculating the Z base is all based on the voltages as well as your single power base. It's not based on any of the currents. If I need to, if I'm in step 4, and if I need to calculate I base, then I can just take V base and divide it by Z base, or I can do S base divided by V base. It doesn't matter. Either one will go from there. And then I'm ready to go ahead and convert my per unit diagram, my impedance diagram, into what we call a per unit diagram. Per unit diagram, this is my impedance diagram. My per unit diagram would look like this. So this is XG1, XT1, X line 1, XT2, and either X load or X, if you have more transmission lines, you go from there. But all your transformers aren't shown on this diagram because they don't do anything with us when we're doing it per unit. This red thing in the bottom is very, very important. It tells you that your base quantities are all scalar quantities. What does a scalar quantity do? Remember, we're talking about complex numbers that have magnitude and angle. So when you're dividing by your base quantities, you are not changing any angles. You are only changing magnitudes. Okay? So SB, VB, IB, and ZB are all scalar numbers. So my power base, I already said, was 100 MVA, right? Not 100 MVA at an angle of 0.8, a power factor of 0.8. It's just 100 MVA. Same thing with V base. I said it was 100 kV. It wasn't 100 kV at an angle of 20. Z base is going to be the same thing. It's just going to be an impedance. It's going to be 5 ohms, not 5 plus J, 7 ohms. And IB is going to be 300 amps, not 300 at an angle of 23 amps. So all your base quantities need to be scalar numbers only. Yes, sir.
In your diagram, an XT1, right?
This is T1, yeah.
XT1, and then if T1 is step down transformer, which means
It's probably a step up transformer.
even if it's a step up, right? Oh yeah,
Yep. That's my generator. It
Yes.
steps up the voltage, most likely.
Now, if on the right side we have, let's say we have 13 kV, that means that going downstream is probably 13 kV all the way down.
So you're saying this actual voltage is here?
Yeah, everything down there is still 13 kV from the other side.
Well, if you're picking V base over here,
Mhm.
then you're gonna calculate V base over here, we'll call it V base two. By using the turns ratio, so that's gonna be equal to VB1 times the A of the transformer two, right? The turns ratio associated with transformer number two.
Mhm.
So you just reflect the impedances, the voltages through the transformers using the turns ratio. That's all you need to do.
So then we don't use the temperature anymore. With the
You don't use what?
The term ratio with the per unit, we don't need the term ratio, right? Using the per unit
The term issue?
term ratio.
Oh, the turns ratio.
Yeah.
No, you do not need to use those. Yep. No, because that's already taken into account for you. And once you're in per unit land, right, there are no more transformers. This diagram, you can see, do I see a single transformer in here? I see a bunch of impedances, and some of those reflect the impedance inside of my transformer, but there's no actual transformers there. So in your per unit diagram, transformers don't exist.
Now, how do you know what is the nominal voltage?
What is the what?
What's the voltage for the line?
What line? The transmission line?
Yeah. How do you know what's the nominal voltage? The
So-
maximum voltage?
It's not the maximum voltage. The line voltage, if you're doing it per unit, is you're picking a V base over here, and then you have to calculate your per unit base voltage on the high side of the transformer or at the transmission line. So it's calculated based on the one that you picked. You generally like to pick some of them that are close to nominal. So if you have a generator that's operating at 13.8 kV, it generally does not make sense to specify or just select a base voltage that is 1000 kV because you're going to get pretty weird numbers. Normally you predict you get as close to the nominal voltage on either the generator or the transformer that you're going to get, but you can only pick one. Sometimes transformers don't match. The base voltage is not going to be the same as the ratio voltage, but they generally tend to be pretty close. Okay. All right. So now when you are done with your base selection, everything's been converted to per unit. Now you do your solution. And Ohm's law, KVL, KCL, superposition, max power transfer, any other ones that I'm missing that you love in theorems?
Voltage?
Norton, Thevenin, all those are valid in per unit. It's just circuit analysis without transformers. So all those theorems are still applicable, but you're not using quantities with units. Okay. And so you do whatever you want to do. You solve for a voltage, you solve for a current, you solve for a power in per unit. And then if you want to, you can convert back to actual ohms or volts or power. You almost never convert back to volts because why do I care that the voltage is 137.29 kV? I'm more interested in the voltage of being 0.993 of per unit. That tells me it's pretty close to what it normally is. So if the voltage is 0.8, then I got a problem. That's a pretty serious voltage drop in my system, so I probably need to start looking at it. So generally speaking, voltages you leave as per unit quantities. Power, sometimes you will convert those back to megawatts or MVA. Current, you almost always convert that back to current, because most of the time when you do fault analysis, you might have something that's 75,000 amps, and that's way above the per unit values, right? The per unit base quantities. So you might have a per unit value that's 22 times its per unit value. So you wouldn't want to, that doesn't give you a lot of information. So most of the time when we look at this system and we're analyzing the system, unless we're looking at things purely from like an overload perspective, not a fault, but an overload perspective, we may want to look at the current, but oftentimes we look at it in terms of power. Are you moving more than, let's say, 2,000 megawatts through that new DC transmission line? If you're pushing 5,000 megawatts, okay, you got a problem. Or what's more indicative is the voltage at one end of the line is like 0.7 and the other end of the line is like 0.95. That's a huge voltage drop in your system, which usually means you get some major problems in your system. So that's why we try to do as much as we can and leave the data in per unit. All right. Take a look at an example. So we have a very simple single phase system here. We have a generator, single phase generator cranking out at 8 kV, and we're going to pick it to be its reference. So we're going to pick it to be at an angle of 0. Its internal impedance or the transformer impedance, you can take your pick, probably we'll call it transformer impedance. Well, transformer, the internal impedance equivalent is 1 ohm inductive. Then we're going to step that up to our transmission line. So we're going to step up of our 8 kV line to a nominal 80 kV line. Then our transmission line is J24. Then we're going to step that down to deliver to our load. And then our internal transformer impedance there is about the same. It's J1 ohm. And finally, our load is about 10 ohms of resistive load. Remember that ohms tells me that's real power. I'm getting paid on megawatt hours based on that 10 ohm load. Everything else, I'm not getting paid for. Does anybody have any issue with the fact that the transmission line has 24 times the reactance that the transformers have? It's a big number, right? When you think about 24, you don't think that much, but if it's 24 more times, you have any problem with that? Does anybody have any issue with that transmission line being such a large impedance relative to those transformers? Maybe back up. If something that's 24 times greater, does that seem like a big amount? It does to me. So does anybody have any heartburn with that? I don't. Why not? It could be that, but more likely it's too expensive to get that J24 ohms down to J1. You can work to do that, but you got to add bundled conductors. You got to add different spacing. It costs a lot of money to get that J24 ohm. So is a utility going to lose a lot of money? No, because the current over here and the current over here, that's going to be 1/10 the current, isn't it? So even though I'm 24 times the impedance, the power consumed, right? The reactive power that's consumed in that line is going to drop way down because it's I squared times X. And I squared times X is 1/10 times 1/10. You're going to consume 1/100th of the power. Right? So what if it's J24? It actually consumes less reactive power than those transformers. So it's not a big deal. So the owners of the transmission systems don't spend that much time working super duper hard to lower the impedances. That's why anybody here, although you all are pretty young, wasn't that long ago that superconductors. Remember how you heard about all these superconductor stuff? Been around for a while, maybe? Where has that gone? Anywhere? Nowhere. Why not? Because it's not worth the money to put fancy conductors and research on your transmission system when the system doesn't really have that many power losses in there because of transformers. So it doesn't really make sense to do a lot of stuff with superconductors. That doesn't mean they don't have applicability, like in your car, like if you're driving around and you wanted to have less losses because you're pulling 500 amps in your car, because you have an EV car, that's different. But over here, it's small compared to the rest of the system. And nothing is going to fix my J1 ohm resistor in my transformer. The superconductor isn't really going to help with that. So I pick my system base of 100 MVA. And I'm going to pick V base 1 equal to not 8 at an angle of 0, but 8 kV. Now, VB2 is going to be equal to VB1 multiplied by the turns ratio. So that's 80 kV. I calculated that value. I did not you get that value. I didn't get to pick it. I actually calculated it. And over here, VB3 is equal to VB2. Why is it VB2 or not VB1? Why is that VB2 and not VB1? This transformer winding is taking whatever voltages are in this region or in this zone, which in that case is VB2, and bringing that down to our VB3 region. It has nothing to do with VB1. That's one other zone away. So it's VB2 times the turns ratio, 1/5, and that is 16 kV. Okay. So now I'm going to calculate ZB1 over here, which is going to be equal to VB squared. So 8 kV squared divided by 100 MVA. ZB2 is equal to 80 kV squared divided by 100 MVA. And ZB3 is equal to 16 kV squared divided by 100 MVA. All right, so I just calculated those three values based on my system base, my one system base. And you'll notice it's one system base because these all stay the same, right? They're all 100 MVA. There's no change in those S-base values. But my V bases went up and down, so I had to go ahead and calculate different Z bases. Now I can go ahead and convert this to per unit. So I'm going to take this whole voltage, and I'll just write my V base over here. And I'm going to divide that by, so I'll move that up there. So this V in per unit is equal to 8 kV divided by VB1, or it's 1 at an angle of 0. And you'll note it's 1 at an angle of 0 because it's a unitless quantity, right? When I divide 8 kV or 8 at an angle of 0 kV by 8 kV, the kVs will cancel out and I'm left with a unitless quantity. So your per unit stuff is all unitless. You should never have an actual per unit quantity that has a unit associated with it because they divide out. And all your base quantities should have units. Z base is in ohms. S base is in MVA. I base is in amps. All right. But the actual per unit quantities aren't there. So now my diagram becomes this right here is 1 at an angle of 0 divided by 0.64 ohms. That's V base 1. Over here, this is dividing by 64 ohms, which you see I calculated 80 kV squared divided by 100 MVA. And my last one, I'm going to divide that by 2.56 ohms, as well as my load. Okay. This might be another indication of why we have unitless quantities, because if I divided my impedance by J 2.56, my 10 ohm resistor, I should say, by J 2.56, I would not end up with a scalar quantity, right? I would end up with a resistor that has a complex term, which is what I don't want. So I don't want to change anything about these. I still want them to look like resistors. I still want them to look like inductors. So I have no phase shift introduced because of the base quantities. So now I redraw my circuit. This is dividing it by V base. I divided by the Z base in each region. And now I redraw my diagram without any transformers. So now my system that has two transformers and 3 V bases, I'm going to go ahead and have a very simple calculation with no turns ratio involved, right? I don't even have a transformer there. And all the units are in per unit. Yes, sir.
VB1 in the order you want, right?
No.
Because there's VB1, which is A divided by A, which should always be 1.
No. You said VB1, V base 1 is not equal to 1.
Right.
The per unit value may be 1, but it doesn't have to be.
In what case can it be not?
What if you said, okay, it's a 13.8 kV generator and you wanted V base to be 15 kV?
Why?
Because the transformer that that generator connects to is rated 15 kV to, I don't know, 230 kV. So you might be back calculating the V base at that generator because you picked a V base quantity someplace downstream.
So you want the V base to be the highest,
No,
or the lowest, I don't know, how do you pick the V base?
you typically want your quantities, if you can, you want to pick your S base. And so this is just a standardized, most of the time your S base is 100 MVA. That's what just all the ISOs and the utilities want. It's almost always 100 MVA. If you were able to pick your own, usually you pick your S base that your equipment in your system has a similar S base. So let's say you get 10 transformers that are 50 MVA. If you use your 50 MVA, you won't have to convert things so much. And we'll see why that makes sense. For V base, usually you just pick one wherever it's convenient. There's no advantage to picking anything, trying to be selective about it. You can a little bit, but most of the time you can't really do anything. Okay, so now we have the circuit. Let's just do circuit analysis. Everybody's pretty good at KVL and can write a loop equation to solve for the current flowing through the circuit. So 1 at an angle of 0 divided by the sum of the impedances gives me 0.22 at an angle of minus 30.8 per unit, not amps, right? It's per unit. And then if I want to calculate, excuse me, the voltage, the voltage at the load, I'm going to go ahead and take my 1 at an angle of 0 and multiply by the series current, or I subtract the series current, multiplied by the voltage drop that I'm going to see. And what I end up with is 0.859 at an angle of negative 30.8. And the angles are the same. Why are they the same? Because I'm looking at the voltage across the resistor. And what does Eli the Ice say about voltages and currents across the resistors or across any resistor? They are in phase with each other, right? There's no phase shift associated with them. So if I have a series current that has 30.8 degrees on the angle, then I darn well better have a voltage that has 30.8 across it as well, across the resistor as well, because they would not be in phase with each other. Now I'm going to go ahead and calculate the power delivered. And you can do this whatever you want. In this case, it's easy enough to say VI conjugate, or you can go magnitude of V divided by Z. And this is a magnitude term because I'm just getting the per unit loss of the load, right? Which we know is purely resistive. That's 0.189 per unit. And then lastly, how much power is the generator putting out? Well, I've got some power losses in the line, right? Some reactive power losses. So I just do VI conjugate there. That's why you'll see that the current, which has a negative angle, I swap that around because I took the conjugate of the current there, and I end up with 0.22 at an angle of 30.8. So the load, this load power over here, this is equivalent to watts. You'll notice here, this is equivalent to MVA because there's a magnitude and an angle. So it's not purely real. There's an imaginary term, which makes sense because the transformers and the transmission line are consuming reactive power. They've got J1s or J24 to make that work. But that's essentially how you do per unit for a single phase system. The hardest part is just following this approach. You should, photocopy this or whatever, put it on the side when you're doing your homework problems, because it's very confusing to get started at first. But once you do it a few times, it sort of becomes second nature. And I already said, it's a fair amount of work to get here, right? Wouldn't it just be easier to go ahead and reflect the impedance up or down? So let's reflect the impedance up through here and then down through here and do our calculation, because then we already know what the current is, right? The problem is, I know what the current is out of the generator. I don't know what the current is through here. So I don't know what the power at the load is gonna be. I don't know what the line consumes for power. There's a lot of information that is buried in the fact that I've moved or reflected that impedance all the way over to the generator. So why bother absorbing it all into one impedance? Let's just go ahead and calculate it. And the other advantage too is, let's say I want this load to be variable. Just like at your house, right? Remember we talked about the example of lights going on, or people running their washers and dryers. Over time, what you see is that it's actually easier if you have to do 4 calculations, 10 calculations. And when you're doing analysis on a power system, you might do millions and millions of calculations. It just depends on what you're trying to do. So you don't just do one, you do many. And the setup on this takes time, but once you got it set up, your calculations are much, much easier. So again, another huge reason why to do that. If you need it on the back end, you can tell me what the actual voltages are. They are way less useful to get voltages than knowing that the voltage at the line is only 86% of nominal. That right there would tell me I got a problem. Also, the angle is pretty high, negative 30.8. That's a pretty high angle. I know it's a negative number, but it looks fairly high, so that means you might have a fair amount of phase shifting in your system. So I probably wouldn't convert the voltage, the power. Yeah, I'd like to know how many MVA I am, because that's what I get paid on. The generator, I want to know an MVA, because the generator manufacturers, when they sell you a generator, they tell you it's a 20 kV generator that operates at, I don't know, 300 MVA. So you can look at how much that is. 22 is not that heavily loaded. And since our system operators tell us it's 100 MVA, knowing that that's 0.22 doesn't really give us a lot of very useful information about how hard our machine is getting pushed. The current, knowing the current is hit or miss. It's probably not that interesting unless you're trying to set up your initial circuit. So if you're building a circuit and you need to make sure that your transmission line isn't going to be overloaded, I don't want to run more than 3,000 amps through there. You may want to go ahead and calculate what that is. But you can see the actual current in the middle is only 275 amps, quite a bit less. Can you do a quick calculation and tell me what the current is coming out of the generator? 30 seconds. Go. Nobody? How would you calculate the current out of the generator?
Yeah, the turn ratio.
I have the turns ratio.
I think it's why is it not defined by I family constant ratio?
Is that correct? Is he right? He certainly could do that, but remember this current right here, the 0.22 at an angle of minus 30.8, that lives everywhere in this series circuit. So if I want to find I actual at the generator, I take my 0.22 at an angle of minus 30.8, and then I multiply that by 100 MVA over 8 kV. This right here is I base at the generator, right? So you can certainly use the turns ratio, or I can just directly get that number. So if I do that, I can see that I got 0.22, and I'm just going to do magnitude only, because we know the angle. 0.22 times 100 E6 divided by 8 E3. So 2,750 amps coming out of the generator, which seems like a lot, but it's not that much for a typical generator. Like I said, there's the one in Millstone Unit 3 is almost 50,000 amps out of that generator when it's all running at full out. Okay, any questions on doing per unit? All right, well, no questions. Let's do the same thing for 3-phase. And we're just going to make 2 minor tweaks. instead of an S base for a single phase system, we're gonna use a 3-phase MVA. Okay, which is gonna be 3 times the single phase value. So that would be 100 MVA. Then we're gonna go ahead and pick a V base for 1 point on the system, but that's gonna be a line-to-line voltage. In a single phase voltage, it was a system is a phase voltage. Over here, it's a line voltage. And we still have to calculate ZB. But do we calculate ZB on a 3-phase basis or a single phase basis? Single phase basis, because there's no such thing as a 3-phase resistor. There are 3 single phase resistors. So if you want to convert a single phase ohm value to per unit, this has to be a single phase value. And you can see when I plug in V base squared, that's a line-to-line voltage. I divide that by S base. My line voltage, I can get that from my phase voltage by multiplying by the square root of 3. And my S base for 3-phase is just 3 times the single phase base. And when I plug those values in, this square root of 3, which is squared, will cancel out that 3 term. So what I end up with is exactly what I had for single phase system. It's going to be VB squared phase divided by S single phase. Right? There's no difference. As long as with 3-phase systems, you use those 2 criteria, you don't have to do any calculation. If you use a different set of criteria, you're going to have to start multiplying or dividing by the square root of 3 to get good results. Our 3-phase system, same process. You can see our S 3-phase system is going to be equal to, if I'm trying to convert to a single phase quantity, I've got 3 times my S base for a single phase. Then I've got square root of 3 times my line-to-line voltage. But if I substitute in my line to neutral voltage, I've got another square root of 3, and the terms will cancel out. So the only thing I have to be careful of with working with 3-phase systems is I've got to include that square root of 3 term for my I. So if I don't, if I pick V base that is a line-to-line voltage and S base it's a 3-phase, I still need to make sure I'm dividing by the square root of 3, okay, to calculate what my current base is. That's a highlight because oftentimes you forget that square root of 3 term, okay? There's nothing we can do to substitute in, so we're stuck with having to include that square root of 3. But that's the only modification we need to make for 3-phase systems. We have to add the square root of 3 term in there. And then all the work is the same. So let's do the, go ahead.
Why or
Doesn't matter. Nope. Because if you remember in a Y, let's go ahead and do S 3-phase is equal to 3 V phase times I phase, right? Correct? Well, in a Y, we know that V line equals square root of 3 times V phase. This is for a Y. For a delta, we know that I line equals the square root of 3 times I phase, right? So in either system, if we use this equation here, right, it works out for all systems. It's either going to work out because in a Y, we know that I line and I phase are the same, but V line and V phase are off by the square root of 3. So I got to have my square root of 3 there. In a delta, we know that I line is off by the square root of 3 from I phase, but V line and V phase are the same. So this equation right here is way more useful to use because I don't have to keep track. Am I dealing with phase quantities or line quantities? The second one, square root of 3, V line, I line, it always works out in the wash because if the voltage is off by the square root of 3, the current will balance things out for you. So that's why we can use it without having to worry about it. So let's redo this problem that we just did. And everything's the same, but now it's a 3-phase system. So we have to convert our line voltages multiplying by the square root of 3. So that generator that was 8 kV now becomes 13.8 kV because it was a phase voltage. Now it's a line voltage. Our power base was 100 MVA for single phase. Now it has to be 3 times that because we have 3 systems that are exactly the same. So that becomes 300 kV, 300 MVA. Our center transmission line, which had a single phase base voltage of 80 kV, is now 138 kV. And our last one, which had a single phase per unit or single phase base voltage of 16 kV, now becomes 27.6 because again, we need to multiply that by the square root of 3. And when we do our calculations, you get exactly the same numbers in our per unit diagram, because this should be a single phase representation of our system. So it can represent a 3-phase, but it's a single phase representation. So the other 2 phases look exactly the same with these. And that's why when you calculate power, you're multiplying by 300 MVA. When you're trying to calculate voltage, you've got to have that square root of 3 term in there. That boosts it up. But the calculations are the same. This has to be a single phase calculation. You cannot calculate your numbers in 3-phase land. You have to go to single phase equivalents. Okay. That's one of the hardest things about working with 3-phase systems is you just think, well, it's a 3-phase system. How do I do the calculation? As long as you convert it to single phase equivalent, which means all those impedances are actual resistors, inductors, or capacitors, those are actual ohmic values. When we adjust our voltages and our power, that will take into account how the system is configured delta or Y. And that will help us get through that. Questions on that? Because our system here is all the same. Remember how before we had our load was 0.189? So that was, what does that work out to be like 18.9 MVA or megawatts? Over here, I'm going to multiply by 300 MVA. Previously, I multiplied by 100 MVA. Since I have 3 exact systems, and each one of those systems is doing 0.81 times 100 MVA, or I can say that the total of the 3 phases is going to be 0.81 times 300 MVA. So what's way more interesting to me is to know what the total system is consuming. Because when I go buy a 100 horsepower motor and I'm in the pulp and paper industry and I'm trying to drive a pump, that 100 horsepower is a 3-phase rating. It is not a single phase rating. Anybody going to guess as to why? No guesses? What about our mechanical engineering friends? Do they care that that motor has a single phase output of 33.3? Or do they really care what's on the shaft, what's available for power? There's only one shaft, isn't there? Last time I checked, they don't make motors with 3 shafts. They make motor with a single shaft. And that total mechanical equivalent power is 100 horsepower. Not 3 shafts putting out 33.3, 1. So our loads, we're always talking about it as a combined load. 100 MVA, 100 horsepower, et cetera, et cetera. We don't care about single phase ones. The only time we care about single phase is like in here in this room. We've got a bunch of lights. We've got some stuff plugged in. Those would be single phase. And so those have to be treated differently. But this room probably doesn't have 3-phase power into it. Most likely. Even though in the basement down below, we do have tons and tons of 3-phase. Does ECE have 3-phase upstairs? Do you know? They actually can, but I don't think they use it for anything because they don't need it. But if you look in some of those patch panels outside of Andy's office, they have 3-phase available. You can all plug it into the basement. In our lab in the basement, we need a lot of it. So we've got all kinds of 3-phase downstairs. It's just 208. It's just not that crazy of a voltage. Questions on that? So here are the voltages and powers, right? So we're just going, voltages are square root of 3 in magnitude, but the angles are the same. Powers now are multiplied by a factor of 3. So we're no longer 18.9, we're 56.7. Or the generator, which we had 22, now it's 66. But the angles are the same. The current is identical. And the reason why the current is identical is we'll set up this as a Y system. So phase currents and line currents are exactly the same. So that's why we get in the middle on our transmission line, we get 275 at an angle of 30.8 amps. Right? That current doesn't change. All right, I'll give you 5 minutes. Oops. Try this problem. Just do the basics. Set up your base quantities, what they should be. If you're not writing, does that mean it's reasonable to assume you're done and I can ask you to present your work? All right. Got a yes? One more minute. Meeting is being transcribed. Perfect. By the way, if you're watching it on YouTube, you can turn on closed captioning if you can't make out stuff. And it actually does a pretty good job. I don't know if anybody's done that, but if you're a little hard of hearing, the closed captioning feature in Google does generally a good job. Obviously, there's some terminology it misses, but it's way better than it used to be. Okay. Anybody want to put up how they did this? Nobody? Why is that? Are you not confident? It's okay if you're not.
So as the single thing, do you get the magnitude of 25/3?
Say that again?
Find the S phase single phase. You take the magnitude of the 100 J/3.
Nope. It's a three-phase load, so why would you want to do single phase? This is a three-phase system, so I'm going to do everything in three phase, which means I'm going to use a three-phase S base. Right? And my voltages are going to be line-to-line voltages. So I'm going to pick VB over here. Oop, sorry about that. Why not just make it 69 kV? Make it an easy calculation. Which means over here, that's pretty easy, right? And then my three-phase S base. Why did I pick three-phase S base of 100 MVA? Because the power, I can also convert that to per unit, right? So the power going over here is going to be 100 plus J50 divided by 100, right? So 1 plus J.5. Why make the calculations hard, right? Why not make them easy? So now all I have to do is calculate what Z base is over here. So that's V base squared divided by S base. And the same thing over here. Now I got a series circuit. Don't I? Why did I pick the 100 MVA? Because I'm lazy. Pretty easy to divide 100 plus J50 by 100, right?
Just choosing yourself.
Generally speaking, you're going to be working with 100 MVA if you work at the utility level. But if you're doing it on your homework, unless I tell you otherwise, you can pick whatever you want. I just picked 100 because it's a very easy calculation. I could have picked 1 if I wanted to, but it might make my numbers a little bit big. So why not just go with 100 and see if I get smaller numbers from there? So now my voltage at my generator or my source is going to be equal to the current, the current I to the load is going to be equal to S equals VI conjugate. So it's 1 plus J.5 conjugated, right? Divided by the square root of 3. What's the voltage over here? In per unit, it's 1 at an angle of 0, isn't it? That's my load current, right? S equals VI conjugate. So 1.J5. I'm so sorry. 1 plus J5 conjugate divided by 1 at an angle of 0. Don't forget, we have to have that square root of 3 term in there. Equals I load, all in per unit. And then my V of my source is going to be equal to 69 kV at an angle of 0. Not right, is that? It is 1 at an angle of 0 because I'm doing it in per unit, right? plus this current, so I load, multiplied by, we'll call this the line impedance, after we convert it to per unit, plus ZJ4 converted to per unit. That's going to give me a V that's actually in per unit. Then to get this final answer right here, this S, I'm just going to go S equals square root of 3 times V source times, oops, the conjugate of I, and then I multiply that by S base. And that's the process to go ahead and solve for that. Okay. Anybody want to see this done in actual calculations, or they feel like they can do it from here? Do a calculation? Sure. As long as nobody has any heartburn with me doing it in MATLAB. So the first thing I'm going to do is I load. That's going to be equal to, and MATLAB has a conjugate feature built in. So if for some reason you forget how to take the complex conjugate of an angle, you can go ahead and just use the conjugate function in MATLAB. Divide that by square root of 3 times 1 at an angle 0, which is just the square root of 3. So my I load, oops, I forgot to close it, is equal to that. So now I have my I load. If I want to solve for I out of the source, right? My I source, and that's going to be actual, is going to be equal to my load current, right? Multiplied by I base at the generator. So I base at the generator is SB. So that's going to be equal to 100 E6, which is 100 MVA. And I'm going to divide 100 E6 by the voltage at that end. So that's going to be equal to 138. Is it 138 kV? I think it's 138. But don't forget, I still need to multiply that by the square root of 3. What am I missing? I missed a parentheses, sorry. And then I'm just going to make it display. And that's going to be, I'm just going to go ahead and put the absolute value of I source. Why am I getting 467 versus 270? If I do display I times the square root of 3, I get the 467. I think I forgot to divide. I think this should be 267 or 270 because I forgot to divide by the square root of 3. So that really should be 270. And then my power is just going to be, or my voltage at my source is going to be VS is going to be equal to 1, which is 1 at an angle of 0, plus my I load times, and this is going to be a little bit messy, so I apologize. So I have to do a lot of, so this is going to be 5.06. Well, actually, you know what? Let me just do it this way. It's going to get too busy. So I'll go Z of my line is equal to 5.06 plus J times 23.7. And I get to divide that by S base of Z base, which is 138 kV squared. And then I divide that by S base, which is just 100. What am I missing here? I get an extra bracket. So that's my Z line. And then my load. So I'm just going to copy this up and I'm just going to make the calculation easy. Whoops. So Z load, that's J4. I think it's J4. So J4 divided by, this now is 69 kV, right? Divided by 100 MVA. And so now my V source is equal to my 1 at an angle of 0 plus my voltage drops in my system. So that's I load times Z line plus Z load. Is it capital I load? Yeah, capital I load, which gives me that value for VS right there. Then I'm going to solve for S of my source, which is going to be equal to the square root of 3 times VS times the conjugate of I load. So 1.019. So the numbers are off a little bit, probably because of the precision. Because when I multiply those by 100, I get 101.9 versus 103.3. This is a little further off, but it's 65. So it's reasonably close because I'm doing everything in MATLAB and making it hopefully more efficient. Well, that's it. That's how you convert back and forth. Okay. Questions on that? Because we'll be doing a lot of per unit stuff in this class. If you buy a piece of equipment that doesn't have an S base or a V base that matches, this equation right here is what you should memorize. If you want to convert, when you buy a transformer, right? And remember when we looked at our transformer over here, this has this 9.36 is based on that MVA, and the voltage is either 115 kV or 35.45 kV. Just depends on which side of the transformer is. If those don't match your actual system, the ones that you use for your system, you got to convert those. So you have to multiply to go from original, you actually convert those to actual by just multiplying by your original Z base. And then you divide by your new Z base. Well, this last equation here has it all in one fell swoop. You just need to identify what is old or original and what is new. And this will save you a lot of work. Remember when we said, well, how do you pick your S bases and V bases? You pick them sometimes so that you can minimize the number of conversions you need to use. But this formula is very helpful, very efficient for going ahead and solving for that. If you have a leakage reactance, which is just the value of X in our equivalent circuit, so that would be your transformer, right? Without any resistors. So that's our transformer. You can convert 3.69, which is on a 54 MVA base. So the transformer is 54 MVA. I want to convert that to 100 MVA base. So I'm going to use this equation here. I don't know the voltages, so I can't use that. So I multiply by ZB new over ZB old, 100 over 54, and I get a 0.0683 per unit for that transformer. So on your new transformer diagram, it's going to look like a bigger number, which makes sense, right? Because a smaller transformer has to have a higher impedance when you reflect it to a higher base quantity. So that's how you would do conversions. This doesn't include voltage, but again, that's just, matching up your V bases and then just putting in VB new and VB old correctly. Let's see. This is the same process, right? A 350 MVA, 230. 230 to 20 kV transformer has a leakage reactance of 10%. What is the per unit value on 100 MVA base? So that 10% becomes 2.86% because it's a 350 MVA transformer moving to 100 MVA. So it should look like a smaller impedance. If I was curious what the value would be, what the actual leakage reactance would be in ohms, I need to know which side I'm reflecting that impedance on. I'm reflecting that to the 230 kV side. So you'll notice that when I say 15.1 ohms on the 230 kV side, if you wanted it on the 20 kV side, this number comes down here, but then you multiply that by 20 kV squared instead of 200. And again, that number is going to look a lot higher because, I mean, a lot lower. Because at 20,000 volts, it should look like a lower impedance than at 230. And this is a generator project I did. It's been a few years now, but this is a generator that goes up in Millinocket. And if you take a look at it, there are all kinds of impedance data located or given to you in per unit. So the voltage is here and the power is here. This per unit quantity, you can see it says the motor parameters and all that stuff. How do you think they got 12.2? Well, let's take a look. Z base is equal to V base squared. So that's 6,900 squared divided by 3.9 M. So let's plug that into our calculator. And 6.9 squared divided by 3.9 e to the 6. What do you know? Equals 12.21. I guess they didn't use MATLAB, so they were off by a little bit. But how they got that ohmic value, see this is base ohms, that's just based on the nameplate rating of the generator. So all these impedances here, right? All those are all in per unit. There are no ohms there. These values are not, right? Because those are in time, right? Those are in seconds. So you don't per unitize seconds when you're talking about time constants, but you can take a look at a typical generator manufacturer's data sheet, and you can actually see that that data is consistent with what we expect. Questions? We have a lab on Monday. We'll go over per unit, right? So you may want to take a look at the pre-lab video. It's totally up to you. But take a look at the pre-lab. You can always come, but the more you come prepared, or if you feel comfortable, you can do it at your leisure, and you can do something else during Monday at lab. I try to empower you all because almost all of you are seniors. So, I give you as much information as possible. You figure out which is the best way for you to learn. So if you prefer doing your lab in a quiet environment, be my guest. If you want to come to lab and get rowdy with me, you can do that too. All right, any questions from TV land or anything like that? We covered a lot of material, but hopefully it's good stuff. Nothing? All right, well, if nobody has any questions, have a great weekend. I'll see you all on Monday. Take care, everyone.